Welcome to Deep Engineering's YouTube channel, where we bring you real-world insights from the engineers and authors shaping modern software. Today, we are speaking with Mihalis Tsoukalos, a Unix systems engineer and prolific technical author whose books Go Systems Programming and Mastering Go have become essential reading for systems professionals working with Go and Linux. Mihalis holds a BSc in mathematics from the University of Patras and an MSc in IT from University College London. He's contributed to publications like Linux Journal, Usenix Login, and CC++ Users Journal, and brings deep expertise in systems programming, time series data, and databases. He's here with us today to talk about the fourth edition of Mastering Go, but more broadly about the state of Go today, what's changing, what matters, and how experienced developers can write more robust performance software using the language. So a very warm welcome to you, Mihalis. It's a pleasure to have you with us today.
Likewise, thank you very, very much for the invitation.
So let's get started with the first question. And I want to start by asking you, what motivated you to write the fourth edition of Mastering Go? Who should pick it up, and what kind of projects will the book help them with?
Yes, first of all, I want to start with a disclaimer that nothing, no book or whatever other resource can, replace experience. So, you have to try things. That's the general idea, and that's why I wrote the book, just to make you try things. But okay, let me continue by answering your question. The main reason for the fourth edition of Mastering Go was the continued growth and evolution of Go. Since the last edition, the language has seen some major changes. The most important change was the addition of generics in Go 1.18. That was a long-awaited feature that really shifted how developers think about type safety and code reuse. Alongside that, we have had improvements to modules, better WebAssembly support, and lots of enhancements across the standard library and toolchain, and as well as fuzz testing for the testing process. So it made perfect sense to update the book to reflect where Go is today. Another big motivator was the feedback from the Go community. Mastering Go has always aimed to be a practical, hands-on guide, and readers kept asking for more real-world examples, especially around things like concurrency, networking, and systems-level programming. This edition builds on that by going deeper into those topics and refining the guidance on writing idiomatic, maintainable Go code. Again, I have to say that again, nothing can replace experience. You have to try things all the time. That's the point of learning something new. The book is best suited for intermediate to advanced developers, mostly people who already understand the basics of programming and want to work with Go and take their skills further. It is particularly useful for engineers working on back-end systems, command line infrastructure tools, high-performance networked applications, or cloud-native services. It is also a solid resource for developers coming from languages like C or C++, Java, or Python, who want to build scalable, efficient systems in Go. For example, it can be used in the following projects: a payments platform migrating from Node.js to Go to reduce latency in transaction processing and better handle traffic; in writing a custom reverse proxy in Go to maximize performance and manage connection concurrency efficiently; or an observability team building high throughput log collectors or trace aggregators that must process and forward millions of events per second. So overall, this edition is not a minor update. It's a reflection of how far Go has come as a language and how central it is becoming in areas like cloud computing, DevOps, and systems engineering. It is really for anyone serious about mastering Go and using it to build high-performance real-world applications.
Right, brilliant. Now let's shift to talking a little bit about, the most recent evolutions in Go. So today, Go's concurrency model remains a major draw. with Go 1.22 fixing the long-standing loop variable capture issue, how do you now recommend structuring Go routines and channels to avoid common bugs?
Yes, the concurrency model of Go has always been one of its strongest features because it's simple, easy to understand, yet powerful. It's not that, I mean, you can have everything, but what Go can do is pretty much what programmers want. Go routines are lightweight. Channels give you a clear way to coordinate between them, and it is generally easy to express concurrent logic in a readable way. But you can always go wrong, especially when we are working on more complex or high performance systems. So one issue that has tripped up a lot of developers over the years was the loop variable capture problem. If you launch Go routines inside the loop, you could accidentally end up capturing the loop variable in a closure, which meant that all your Go routines might reference the same variable, not what you intended. You usually want to each Go routine to take a different variable value. The typical workaround was to reassign the variable inside the loop, but it was error prone, and you know it was an issue. It was an issue. With Go 1.22, that was finally been fixed. Now the language create a new instance of the loop variable on each iteration, so closures and Go routines get the correct value automatically. It is a small change in behavior, but it eliminates a very common class of bugs and makes concurrent code cleaner and more predictable. That said, even with this fix in place, you will still need to be, you know, to be cautious and think about it when writing concurrent code. A few best practices. I mean, let me now list some best practices. First, always be explicit about Go routine ownership and lifecycle. The way to do that is by using context. Dot context. The name of the package is context, you should use the context data type to manage cancellation and timeouts. This is one of the best ways to make sure Go routines do not hang around longer than they should. This way you avoid memory leaks and unpredictable behavior. Second, you can limit concurrency when needed. I mean, just because Go routines are lightweight does not mean that you should, use thousands of them without thinking about the problem. If you are processing a large number of tasks or input-output operation, then you can use worker pools, semaphores, or bounding channels to keep things under control. Another tip is to avoid unbuffered channels for high volume communication. They are great for synchronization, but if you are passing a lot of data around, buffer channels help reduce blocking and improve performance. Again, think about it before you start writing. I mean, sometimes uh, good planning can save you from bugs and from bad design. And the last tip is to always close channels properly. Only the sender should close a channel, and only once this should be done. Closing channels for multiple places or from the receiver side can cause panics or race conditions, and this is, as you can understand, a bad thing. It is also a good idea to use the select statement defensively, especially when working with multiple channels. A default case can help you avoid blocking in situations where responsiveness matters, like in event loops or fault-tolerant systems. And finally, do not force everything through channels. In general, if you can avoid using channels, then use that method. I mean, don't use channels all the time. Although the channels look practical at first, uh, usually you can use another way to do that. Sometimes mutexes or atomic operations are a better fit. So think about it before you start writing code and designing your program. So overall, Go 1.22 makes life easier for concurrent programming, but writing robust concurrent code still requires discipline, clear design, and a good understanding of how goroutines and channels behave under the hood. This is what really helps you build systems that are both maintainable and production ready. Again, think about it before you start writing the code, and don't just throw, goroutines because they are lightweight.
Got it. Okay, moving on from there. When you think about concurrency at a systems level, which patterns do you find most effective for real world workloads? Are there particular idioms you sort of keep returning to, like worker pools or pipelines?
Yes. At the systems level, concurrency is not just a feature, it's a design principle. It influences how your software scales, how efficiently it uses resources, and how it behaves under pressure. So, Go gives you the primitives, Go routines and channels, but using them well requires a solid set of patterns you can rely on. So let us list some of the patterns. First are worker pools. They are probably the most universally effective pattern. Unix, the Apache web server used to do that with threads. Instead of spawning a new Go routine for every task, you maintain a fixed set of workers that pull from a task queue. This gives you control concurrency. You are not, overloading the system with thousands of Go routines, and you are staying with the limits of things like memory, file descriptors, or database connections. So this makes the behavior of the system under load much more predictable because you know what you are using. I mean, if you are just spawning Go routines, you don't know how many you have active. Okay. For example, on a project I was working, we used worker pools in a log processing service that handled thousands of files per hour without any issues. So the second pattern is pipelines. So these are great when you want to break a task into stages and process each stage concurrently. Each stage runs in its own coroutine and passes data to the next using a channel. It is a clean way to handle streaming data, transformations, or multi-step processing. It uh, it, it encourages modularity and make it easier to deal with back pressure and separation of concerns. So as we mentioned earlier, there is also context. I mean, the context package and the context data type, which I consider non-negotiable in any serious concurrent Go application. It is the standard way to manage timeouts, cancellations, and deadlines across Go routines. If you are handling HTTP requests, running background jobs, or coordinating distributed tasks, context helps you shut things down cleanly and avoid Go routine leaks. This is especially important when you are interacting with external systems like databases or APIs, where you do not want calls hanging without finishing. That will cause, like if you are writing a TCP server and connections are not closed properly, you might end up not having enough ports to serve new connections. Another pattern I use is fan out, fan in. Fan out means launching multiple Go routines to handle parts of a job in parallel. And fan in means collecting the results into a single place, combined with worker pools. This is a powerful way to parallelize work and aggregate the results efficiently. Again, you have control of what is going on. I used this the fan out fan in pattern for building a monitoring aggregator service with lots of microservices for help and metrics data. Some of them over HTTP, and then I collected the results into a single response. I also like working with select statements, being able to multiplex across multiple channels or listen for a cancellation signal or timeout is incredibly powerful. It helps you write responsive systems that can recover from delays, retry on failure, or timeout gracefully. One principle I have gone to follow over time is do not reach for channels by default. I discussed that before. Do not use channels by default. Just think about it. Usually, you do not have to use channels. As I told you earlier, a mutex or an atomic operation might be more appropriate and create a simpler, cleaner, and less error-prone design. Okay, and finally, goroutine supervision is critical. You need to track what your goroutines are doing, make sure that they shut down cleanly, and prevent them from existing in the background and without doing anything. So, to sum up, the patterns are worker pools, pipelines, the context package, fan in, fan out, and select statements. This will help you create really good Go code.
Right. Okay. Thank you for that. Moving on to our next question. Let's talk about Go's runtime performance, which has improved noticeably. Tail latencies are down, and the garbage collector is smarter. What profiling techniques do you recommend to help teams actually realize these gains?
That's a good question, because sometimes you have issues and you don't know how to discover what's going on behind the scenes. So Go has made real progress on runtime performance. The garbage collector, in particular, has seen big gains in terms of post times and CPU usage. Again, if you don't know about that, the garbage collector is running as a goroutine. Okay, so everything goes a goroutine, including the garbage collector. The special thing about the garbage collector is that sometimes for the garbage collector to operate, everything else must freeze for a little while, because you cannot create new variables in the garbage, and while the garbage collector is cleaning up things. So tail latencies have also come down, which makes Go a strong option for performance-sensitive systems like APIs, proxies, and backend infrastructure. But those gains do not happen on their own. You need to profile and measure to benefit from them. Optimization without measurement is really, guesswork. It's like guessing what is happening. But the thing is that Go gives you excellent tools for profiling, and with the right approach, those tools can lead you to real improvements. Just, again, something practical that I would like to add here is that don't wait for the problem to come to learn about optimization and measurements. Experiment on your own, and so when the problem comes, you are ready to use the tools. Don't try to use the tools that I'm going to mention for the first time in a real problem, because you are most likely going to mess up things. And a second warning is, be very careful when using such tools on a production system, because you might crash it, and that is not what is usually allowed. But okay.
To avoid that.
Yes, it's especially like you, there's especially on peak hours. Don't use don't use measurement. Don't take measurements or whatever on peak hours, unless you really need to do that. So the first tool that I always recommend is pprof, which is built in and it's powerful. The net HTTP pprof package exposes several types of profiles: CPU, heap, goroutines, blocking operation, mutex contention, and you can access all of them through an HTTP endpoint, meaning your web browser. Then you can visualize them using GoTool pprof or one of the newer web interfaces. I usually recommend to start with CPU profiles. Run them under a realistic load and see where your code is spending time. It is often not where you expect. And also, heap profiles are just as important, especially now that the garbage collector is more efficient. If you can cut down unnecessary allocations, the garbage collector has less stuff to clean up and your applications run more smoothly. One common mistake is only profiling using benchmarks or local tests. But the thing is that you need to profile real workloads in production in a staging environment that mimics production closely. Again, ask if you are allowed to do your testing in production. Don't try things in production without, everyone else knowing that. And don't use the peak hour. Just use common sense. Think about it and decide what you can do. I usually recommend having a staging environment or a testing computer that you can try things. Um, but at the end of the day, the patterns you see in local tests often do not reflect what really happens under real traffic. So many teams now include pprof endpoints in production behind secure admin-only routes so they can safely collect data without, bothering the users. So after that, for deeper insight, I recommend running runtime tracing. So the runtime trace package of the standard library gives you a timeline of goroutine scheduling, system calls, input-output events, garbage collection, only in one place. When paired with pprof, it helps explain why goroutine was delayed or what caused the latency spike. You can collect traces with go test minus trace via code and then explore them with go tool trace. If you are doing micro optimizations, Go benchmarking framework is another great tool. Metrics like allocations per operation, bytes per operation, or nanoseconds per operation help you track how small changes affect performance. Especially in tight loops or hot paths like serialization or hashing. Even one extra allocation can have a big impact under heavy load. So it's worth running go test minus bench regularly if you are tuning critical functions. Again, I should say here that you should experiment beforehand. Don't try to learn a tool while there's an issue because you might have problems understanding what's happening. So continuing, it is also important to watch for goroutine leaks or contention. Use goroutine and block profiles to track how many goroutines are running and whether they are getting stuck. If you see the goroutine count slowly rising over time, that is often a sign something is leaking or blocking unexpectedly. Beyond profiling, observability really matters. The teams that do best with performance tend to invest in continuous metrics and dashboards. The key word here is continuous. Getting metrics all the time, even when not needed. Tools like Prometheus, which like a database for data, and in combination with the ability of Go to export metrics, let you track garbage collection, post times, allocation rates, goroutine counts, and more. And if you add the alerting, then you will catch things before they are really can affect the end users, okay, or your boss. Um, and that's a bad thing. I won't go into more detail here, but there are many tools and there are many things that you can try, especially, and I mean, you can trace network calls, database queries, or internal queues, but I mean, that all this depend on the application at hand. One case that happened with the team that I was part of was I was working on a project with a team building a high throughput telemetry pipeline. The team was seeing an unusually high CPU usage during peak hours, although the Go runtime appearing idle most of the time. To to I mean, to make the long story short, the problem was that they are using JSON Marshall all the time inside the loop, and which was allocating and copying far more data than necessary. When we replaced that with a streaming encoder, everything went much faster. So, again, use common sense. If your application is doing lots of JSON processing, you can surely benefit from using a streaming encoder. Okay.
Right. Okay. Thank you for that. And now let's talk about profile guided optimization, which became stable in Go 1.21. So, where does PGO make a real difference, and when might it not be worth the effort?
Yes, the stabilization of profile guided optimization in Go 1.21 was a big milestone for performance-focused developers. Go has traditionally emphasized simplicity, fast compilation of deep compiler optimizations, but PGO, profile-guided optimization, changes that. It gives us a new way to fine-tune performance based on how our code actually runs in production. In simple terms, PGO lets the compiler make smarter decisions using real-world runtime data, things like which functions are called most often, which branches get taken, and where the hot paths. With that information, the compiler can do things like reorder function to improve caching performance, inline code more intelligently, and reduce indirect calls. The result is lower CPU usage and better latency, especially in high throughput or tight loop scenarios. So, where does PGO shine? It's great for performance critical systems with stable workloads, things like low latency services, backend infrastructure, proxies, or message brokers. In these environments, even a little improvement in CPU can translate into real wins. In also PGO also makes a real difference in hot path code. For example, in tight loops that run millions of times, or in CPU bound routines like encoders, parsers, or math-heavy computations. PGO helps the compiler optimize layout and branching in those areas, which can reduce stalls and improve instruction cache behavior. Um, if you're running a large-scale or long-lived services, even small gains can add up. A 5% CPU saving across hundreds of instances, it's really important. That said, PGO is not always worth the effort. There are some situations where the return just doesn't justify the setup. For instance, if your application has predictable or highly variable workloads, the profile you generate today might not reflect how the application behaves tomorrow. So, you know, it is also PGO is also not ideal for short-lived command line tools or scripts. Another case is early stage development. If your code base is still changing frequently, PGO is premature. Finish your applications and then finalize the code as much as you can, and then you can consider using PGO. In general, that's the idea of PGO. PGO is a powerful tool, but like any optimization technique, it is most effective when used deliberately. If you have already profiled your application, you know where the bottleneck is, and you want to squeeze out more performance without rewriting code, then PGO is a great next step. But again, it cannot solve every possible scenario. I won't go into more detail with PGO as I'm not that experienced, but uh, it's what I mean. The general advice is what I told you before. Experiment with it on your own time, without something real to solve, so you can use that tool when needed.
Right. Now, let's talk about memory. What is your typical workflow for diagnosing memory leaks using high allocation rates in Go systems? Do you have any favorite tools or patterns that you like using?
Okay. Although nowadays computers have more memory, we still need to, to see what is happening. And the most important thing to do is avoid memory leaks and reduce high allocation rates. So when I'm diagnosing memory issues in Go, whether it is a potential leak or just high allocation pressure, the first thing I do is establish a baseline. That means running the service under real world or representative load and collecting memory data that reflects actual behavior, not just synthetic benchmarks, meaning benchmarks with synthetic data, not real data, because you have to know what is happening in reality. From there, I rely heavily on Go built-in tooling, especially pprof. I usually instrument the service with an HTTP endpoint using net HTTP pprof that was mentioned earlier, then capture heap profiles at different points in time, typically one right after startup and another after the service has been running under load. Comparing these snapshots helps answer the key questions. Are allocations growing continuously? What types are taking up the most memory? Is the garbage collector doing more work than expected? So then I will load these profiles into GoTool pprof and or use the web interface, and I focus on views like in use space or in use object. If I'm seeing unexpected memory growth, I look for object types that shouldn't be long lived but are still hanging around, meaning that for object types that a garbage collector cannot clean. I also use the minus alloc space and minus alloc object views to see where allocations are happening most frequently. That helps distinguish between the true leak and just memory from too many short-lived allocations. A common pattern I follow is to take delta comparisons between snapshots. If the memory profile looks flat but allocation counts are high, that's often a sign of churn, not a leak. That's where tools like GoTest minus bench mem come in handy. They let you see allocation behavior in tight loops or hot paths and validate changes quickly. Um, when I'm trying to reduce allocations, I start with escape analysis. Go Cobalius gives you a lot of insight here. If you run go build minus g c flags equals quotes minus m, it will tell you which variables are escaping to the heap and why. Even small changes like passing a pointer instead of a value or using a buffer can keep things on the stack and reduce the garbage collector pressure. If I see repeated allocations of slices, maps, or temporary tracks in performance-sensitive areas, I will look at options like sync.pool or pre-allocating and reusing buffers carefully. Even avoiding repeated string concatenations in loops or unnecessary interface conversions can make a noticeable difference to memory usage and garbage collection overhead. For services that are long running, I also recommend taking full memory dumps periodically and tracking object retention over time. That helps catch leaks caused by forgotten references. You can always and you should always use monitoring tools like Prometheus for storing the data and Grafana for visualizing the data, because you can see things more, more visually. And if on a visualization you see something that was not expected, then you can look into it in more detail and see what's happening. At the end of the day, avoiding memory leaks comes down to habits. Profile early, understand your allocation patterns, do not rely on global state, and monitor in production. It's not just about saving memory, it's about running a system that behaves predictably under load. It doesn't catch you off guard in the middle of the night. There are stories of people waking up in the middle of the night because they are, on a shift and they have to deal with an issue.
Yeah.
again, I'm not going to tell you now a story because I have some stories with with memory leaks, but the thing is that you should know what you are doing, and you should have a good understanding of how your application behaves, where the memory is
Mm.
allocated, where it's freed, and so on.
Right, right. And feel free to share any stories that you can think of throughout. We'd like love to hear.
Uh,
If you,
I will say, but the thing is that yeah, okay. One memorable case involved a team that was seeing their Go service gradually climbing memory usage over several days, even though the load was steady. They suspected a leak, but the garbage collection seemed to be working and they were not seeing out of memory crashes. By capturing and comparing heap profiles over time, they noticed a particular map of cached protobuf messages was never shrinking. Turned out they were using a custom cache with no eviction policy. It was just kept growing. Uh, even what made the situation even worse was that the keys were strings derived from user input, so the cardinality was unbounded. The fix to this situation was introducing a bounding LRU cache with periodic cleanup, but the key insight came from seeing that the live object count of a specific type just kept rising across heap snapshots. Without those profiles, it would have been much harder to pinpoint the issue and of course, correct it.
right, right. Thank you for sharing that, Mihalis.
Yes.
So moving on from that, generics have been around for a couple of releases now. What patterns have you seen work well, and where do you think developers are overusing or misusing them, perhaps?
Now that the generics have had time to mature over a few Go releases, we are starting to see clear patterns around where they really shine and where they tend to go off the rails. One of the most effective use cases has been writing reusable type-safe data structures and algorithms. Things like generic slices, generic sets, generic maps, or utility functions, map, filter, and reduce have become much easier to implement in a way that's both clean and performant. It has led to better library code, especially in packages that deal with collections, number crunching, or parsing. Libraries that used to rely on the empty interface, or in type assertions now benefit from compile time safety with very little extra syntax. That's a big improvement in terms of both correctness and readability. Another area where generics work really well is domain-specific helper functions. For example, a pagination utility that works across different types of records, or a retry wrapper that can handle arbitrary operations. These kinds of generics help eliminate boilerplate and keep APIs consistent without losing clarity. When used truthfully, they make code more declarative and reduce the need for duplicating logic across devices or modules. That said, we have also seen some missteps. A common one is overgeneralization, creating overly abstract, flexible APIs just because the language now allows it. Another pattern to watch out for is wrapping generic types in ways that make the intent not clear. Instead of using a simple slice of type T, developers sometimes introduce unnecessary abstraction that add layers without any real benefit. This makes the code base harder to understand. There is also a tendency among some developers to bring in functional programming paradigms like building nomads or chaining combinators or writing small deeply nested generic utilities. While those patterns can be elegant in languages that are designed for them, they're often clashed with Go core philosophy, clarity, simplicity, and explicit flow control. When these patterns get it ported over without adjusting for Go idioms, the result can be clever looking code that is difficult to read and even harder to debug. So in short, generics are a powerful addition to the language, but like any powerful tool, they need to be used with purpose and restraint. Again, think before you use generics and prefer clear designs. The purpose is to have code that is easy to understand and easy to maintain.
Right, right, got it. So moving on to the next version, Go 1.23 adds iterator functions and generic type aliases. How do you see those changing how we write Go, especially in libraries?
Mhm. So the addition of iterator functions and generic type analysis in Go 1.23 might look like a quiet update, but it is actually a significant step forward in how we can write more expressive, reusable, and composable code, particularly in libraries. These features built on the foundation of generics, and they led to capture common programming patterns more naturally without giving up the core concepts, the core strengths of Go, simplicity and clarity. So, for example, take iterator functions. Go has always relied on for loops and range for iteration, but that worked well. But now with iterator functions, we can encapsulate iteration logic as values, functions that get elements one at a time. That might sound like a small shift, but it opens up some powerful patterns, lazy evaluation, functional style pipelines, and more composable data flows. You are no longer stuck rewriting the same loop boilerplate. You can abstract iteration into helpers that are both type shape and ergonomic. Then there is generic type analysis, which help which help reduce friction when reusing generic types across packages. Before this, if you wanted to tailor a generic type like map, uh, K, and V, or option T to fit your domain, you often had to rewrap or implement it again. That made things verbose and diluted the usefulness of generic libraries. Now, with type analysis that support generics, you can define concise, strongly typed shortcuts for common patterns. This improves readability and makes code easier to work with without introducing any runtime overhead. I think that in libraries, both of these features will lead to more expressive APIs and more composable domain agnostic utility packages. Um, you will probably start seeing libraries that offer richer iterator utilities, things like filter, map, and reduce, model in a way that feels Go native. But again, this is a new feature, and we have to wait for it. The real challenge is for library authors to strike the right balance, using these tools to enhance code, not to overcomplicate it. Uh, if done well, these features could significantly modernize the Go ecosystem, especially in areas like data processing and systems level programming, where usable containers, iterators, and high order utilities really shine.
Okay, thank you for that. Moving on to the next question. Fuzzing is built into Go now. How have you seen teams make fuzz testing practical? And what are some tips to get value from fuzzing beyond, just turn it on?
Yes, fast testing is a powerful technique for uncovering edge cases, subtle bugs, and even security issues. Things that traditional unit tests often miss. So, since Go 1.18 added fuzzing support directly into the Go test tool, we have seen some teams start experimenting with it. Again, it's important to experiment with it first. But as you said, just enabling fuzzing is not enough. To really benefit, teams need to approach it in a focused and deliberate way. The teams that get the most out of fuzz testing usually start by targeting critical code paths, places where the software processes complex or untrusted inputs. Think parsers, codecs, or deserialization logic. These are prime candidates because they are often hard to reason about and easy to break with unexpected input. Again, a note here, never trust input from users. Okay, we have to be very careful with user input. So writing fast tests for those areas helps surface bugs that could otherwise go unnoticed. It is also important to seed the fuzzer well. Instead of letting it start with totally random inputs, you give it examples that are representative of real data. That helps the fuzzing engine explore the space more intelligently and find meaningful failures faster. Integration is key to the most effective teams make fuzz testing part of the CI workflow. Continuous integration. They run short fuzzing sessions locally during development for quick feedback and then schedule longer runs overnight or during off hours on the CI servers. That way, fuzz testing becomes a continuous part of testing, not just something you do once in a while. Um, Beyond just finding crashes, fast testing is great for hardening your error handling. It helps ensure your code does not panic, leak resources, or hang when it gets bad input. And when you run fast tests with other tools like the race detector, you can catch data races that might not show up otherwise. That combination improves readability across the board. Um, again, uh, and now I'm going to offer a tip. Keep your fast functions deterministic and free of side effects. Avoid calling external systems or relying on random behavior inside the test itself. That makes failures easier to reproduce and therefore easier to debug. If you get, if your program do not crash all the time, then it's easier to find the bugs. But if you have deterministic behavior, then you know that there's an issue and you can easily find the issue. Okay, so in short, fast testing becomes truly valuable when it's used deliberately. Targeting the right parts of your code, setting it well, integrating it into your workflows, and combining it with other tools. Done right, it is not just about finding obscure crashes, it's about building more robust, resilient Go systems.
Right. Okay. Moving on to our next question. So, observability is another area you cover in your book. But what do you recommend for monitoring and tracing Go systems effectively, especially under high concurrency?
Yes, observability is absolutely essential when you are running Go systems at scale, especially in high concurrency environment. It's what gives you the visibility to understand how your application behaves in production, diagnose issues quickly, and keep performance and reliability where they need to be. For monitoring, the first step is always to focus on metrics, both system level and application specific metrics. We have mentioned Prometheus before because Prometheus is the go-to choice in the Go ecosystem, largely because it is flexible, it large and its strong community support. The key is to instrument your code with meaningful metrics. I mean, put simply, if you do not collect the appropriate metric, then you are not going to solve your issues. So things you should get metrics like request rates, error counts, latency percentiles, goroutine counts, and garbage collection poses. These tell you how the system is behaving and where things might be starting to degrade under load. You also get a lot of value from the Go runtime metrics exposed through the runtime metrics package. We have mentioned that package before. These give insight into memory usage, garbage collection activity, garbage collector activity, and go routine scheduling. Things that become essentially important when you are dealing with thousands of concurrent operations. So now, while metrics give you a good aggregated view, tracing helps you zoom in. With distributed tracing, using something like OpenTelemetry, you can follow individual requests as they move through different parts of your system. That's where you start to see where latency accumulates, how services interact, or where contention is happening. Under high concurrency, tracing is particularly useful for catching queuing delays, low contention, or slow dependencies, issues that metrics alone might mask. One of the most important practices here is using context propagation correctly. We have mentioned the context.context data type before, and this is your mechanism for passing timeouts, cancellations, and tracing data across APIs, boundaries, and goroutines. If you don't propagate context properly, you will miss spans or lose correlation in your traces. So making sure your instrumentation respects and carries context end-to-end is critical, especially in concurrent workloads where requests may fan out into multiple goroutines. Of course, high concurrency also means you are generating a lot of telemetry data. So you need to be smart about sampling and rate limiting. Adaptive, adaptive sampling is a good approach, prioritizing traces based on latency, error conditions, or unusual behavior. That way, you capture the most informative data without overwhelming your observability systems or introducing overhead. So, but observability is not about collecting data, it's about acting on data. Instead of relying solely on fixed thresholds, use anomaly detections and pattern-based alerts. Dashboards that track those specific behaviors like spikes in goroutines or increased garbage collector poses make it much easier to spot problems early and understand what is really going on. So, in short, effective observability in high concurrency Go systems is about combining detailed metrics, distributed tracing with proper context propagation, smart sampling, and ongoing analysis. When you have those pieces in place, you are in a much better position to detect issues early, debug complex behavior, and keep your systems running smoothly at scale.
The standard library keeps expanding. New utility packages, smarter routing, inlet HTTP. Do these reduce the need for external frameworks? What do you feel is still missing?
So, the standard library of Go has always been one of its stronger features. Clean, composable, and I mean, it's good to have a good and a well-tested and a rich standard library. Um, Over time, the maintainers have added to it in a very deliberate way. Things like smarter routing in net HTTP and new utility packages like slices, maps, and CMP have made it easier to build web services, command line tools, and system level software directly on top of the standard library. And yes, these improvements definitely reducing the need for external frameworks, especially for small to mid-sized applications. One of the best examples is what you have mentioned, Net HTTP, which has seen steady enhancements, better routing logic, smoother integration with middleware patterns, improved support for HTTP two, structured headers, and overall better ergonomics for teams that prioritize simplicity, performance, and long-term maintainability. That's a big win. However, uh, I will return to NetHTTP in a while. Let me continue, and then we will come back to it. The new utility packages help to tasks like filtering, slicing, comparing maps, or writing reusable type-safe logic can now be done concisely and in a go and in the Go way. So you are writing less boilerplate and depending less on external helpers for common operations. That said, while the standard library has come a long way, it does not fully replace the need for third-party libraries, particularly when you are working on more complex systems or domain-specific problems. I have written HTTP services in Go, and I have never used Net HTTP. I I use the Gorilla, if I recall well, I use the Gorilla library, which is really powerful. And for building command line tools, I use Viper, and I mean the Docker tool, the famous Docker tool, has been written in Go using. Let me check if it's indeed Viper Go. The Hugo tool has been the Hugo static website static generator has been implemented using Go and Viper, and these are powerful tools that uh, can write real world utilities. So I think that the standard library cannot get Cobra and Viper. Yes, the other tool is Cobra and Viper. Tools like that are missing from the standard library, but still the standard library is powerful and keep evolving. So I mean, I expect to see more from the standard library of Go, but still there are still things missing. I haven't had the time to experiment with a newer version of net HTTP, but I will do it soon.
Right, right. And now we are moving towards the end of the interview. So, one of the last questions I have for you is even experienced Go developers must make mistakes. And what are some of the less obvious ones you still see when people work on performance sensitive or concurrent systems?
Yes. So everyone makes mistakes, so that's how we learn. So yeah, so that's not bad. But you should be very careful not to make those mistakes on production systems. So even experienced Go developers can run into subtle issues when they are working on performance sensitive or concurrent systems. A lot of that comes down to the simplicity of Go. Go routines are lightweight, channels are first class, and the standard library gives you a lot of powerful tools. But that simplicity can hide complexity, and mistakes often come from relying too much on defaults and making assumptions about how the runtime behaves. One common pitfall is spinning out Go routines without proper cancellation or lifecycle management. We have talked about that before, and we have said that if we properly use context, we can let's say have a better control over the Go routines, and we can properly cancel them and avoid memory leaks. Another mistake is assuming that channels are always the right concurrency primitive. We also discussed about that, and we said that uh, when I first learned about channels, I thought that channels might solve every issue I have with Go routines and concurrency in Go, but that's not the real thing. In some cases, a mutex or an atomic variable might be more efficient and easier to work with than channels. Think about that before using channels. So memory allocation is another big one. Developers often overlook how temporary allocations, like slices creating in a tight loop or boxing values into interfaces, can lead to heavy garbage collection overhead. That gets worse under high concurrency. For such things, tools like pprof or go test minus bench mem help you spot these patterns. But as we said earlier, we should have a really good understanding of the way that our applications work and how they operate and how they create Go routines, how they create slices to be able to avoid such things, especially memory related things by design and not by accident. Another mistake that people do is that they make false assumptions about how the scheduler works. For example, developers sometimes expect Go routines to be preempted fairly, but in CPU-bound loops without any input-output or channel operations, Go routines might not yield control on their own. They can lead to starvation or uneven workload distribution. So newer versions of Go have improved scheduling and preemption, but in rare cases, you still need to explicitly yield with something like runtime dot go scheds to let other Go routines run. So overall, the issues I see are not usually about the syntax. It's about they are about the architecture of the application. They come from assumptions about how Go handles concurrency and performance under the hood. The best way to avoid them is by profiling continuously, testing under realistic loads, and loading a solid mental model of how Go runtime behaves at scale. I mean, know the internals. This means know the internals. Do not assume, just learn the internals of Go well.
Right, right. That makes complete sense. And Mihalis, you've worked very close to the metal for many years now. How would you compare Go and Rust for systems programming, especially in terms of performance, safety, and maintainability?
Yes, I mean, lots of people are asking this
Yeah.
question. Go and Rust take very different approaches to systems programming, and choosing between them really depends on the specific priorities of your project. Rust gives you fine-grained control over memory and concurrency with zero-cost abstractions that can lead to exceptional performance. Its ownership model and borrow checker eliminate entire classes of bugs at compile time, things like data races or use after free errors. But that makes Rust a great choice for low level systems where correctness and reliability are absolutely critical. Think operating system components, device drivers, or performance sensitive network code. But that level of control comes with a steep learning curve. Rust's mental model around ownership, lifetimes, and trade bounds can slow teams down, especially if you are new to the language. Refactoring or prototyping often requires a lot of care to satisfy the compiler, and while Rust tooling like Cargo, Clippy, and Rust Analyzer is excellent, the language itself demands precision. That pays off in terms of safety and performance, but it can be a barrier to in fast-moving or exploratory development environments. Go, by contrast, is all about simplicity and speed of development. Its concurrency model with goroutines and channels is approachable and powerful, and the garbage collector handles memory management, so you do not have to think about it most of the time. Go might not match Rust in terms of raw performance, especially for compute-heavy workloads, but its performance is really consistent and more than good enough for most system-level use cases. The, that predict that predictability combined with Go, with the readability and minimalism of Go, makes it a practical choice for building high throughput services, container tools, infrastructure automation, and other backend heavy systems. It's easy to onboard new developers, and because Go code tends to look the same across teams, long-term maintainability is a real strength. On the safety front, Go does not give you compile time guarantees like Rust does. It won't catch data races before you write your code, but it does offer good tools. The race detector, a solid testing framework, and a culture that values clarity and explicitness. Go avoids a lot of complexity by design, no macro heavy DSLs, no surprising inference, so the code tends to stay understandable even as the system grows. So to sum things up, Rust is the right tool when performance and safety are top priorities, and you are ready to invest in that upfront complexity. Go, on the other hand, shines when development speed, operational simplicity, and long-term maintainability are more important. Uh, some time ago, we evaluated Rust for a inspection engine, but chose Go due to faster development time and easier team onboarding. And the last few months, there is another alternative because I'm always looking for good system programming languages, and
Right.
I think that Go is good, Rust is good, but there's another. The last few months, I got the chance to work with the Zig programming language, which I found very interesting, easier to learn than Rust, and more low level than Go. Maybe Zig is a sweet compromise between Go and Rust when you want to know, to go lower. I mean, when you want to Zig does not have a garbage collector, but you have to manually allocate and deallocate memory, but it's much easier than Rust to learn, and and that's a good thing. I don't like. I tried to learn Rust, but I found it. I don't know. I didn't like it, so I gave up on Rust at the moment.
Okay, final question for our interview. Looking ahead, Mihalis, what are you most excited about in Go's evolution over the next few releases? Where do you see the ecosystem heading?
Looking ahead, what excites me most is how Go continues to evolve in a way that stays true to its roots, pragmatic, simple, but increasingly powerful. One of the areas I'm really watching is the ongoing evolution of generics. Since type parameters were introduced in Go 1.18, each release has built on that foundation, most recently with features like generic type analysis and iterator functions in Go 1.23. These are not flashy changes, but they are meaningful. They are enabling more expressive and reusable code across the ecosystem, richer data structures, functional style APIs, and cleaner abstractions in libraries. What I'm most looking forward to is seeing how the standard library and open source projects embrace these tools to offer more composable idiomatic patterns without losing Go's clarity. Another area that is maturing quickly is performance tuning and runtime observability. Tools like built-in fuzzing, profile-guided optimizations, and expanded runtime metrics are pushing Go beyond just being easy to use. It is becoming easy to optimize too. For teams building high performance systems, this is a big deal. I think we will start to see profiling and performance tuning become a regular part of the development workflow, just like writing tests with better integration and less friction. Concurrency is also evolving, and that's especially important as Go continues to be used in multi-core high-load environments uh, where that's APIs, networking layers, or real-time systems. Go has always had a clean concurrency model, but there is now more attention on things like scheduler improvements, memory footprint reduction, and smarter resource usage. The recent fix to the goroutine loop variable capture bug is a good example. It is a small change, but it addresses a long-standing issue that tripped up even experienced developers. I would love to see more of that, language level improvements that quietly make concurrent programming safer without adding complexity. Beyond the language itself, the ecosystem is maturing. It's maturing fast. We are seeing better libraries, stronger tooling, especially around testing, static analysis, and cross compilation, and an improved development experience overall. Projects like Tiny Go, Go Cloud, and Go growing presence in the WebAssembly and embedded environments point to the future where Go is not just a server-side language anymore. It is becoming part of a broader portable system toolkit. At the same time, efforts around formal APIs, versioning best practices, and module proxy infrastructure show how the Go community is becoming more production hardened and resilient. So in short, I'm excited that Go is getting more powerful without becoming more complicated, which is always which is always the case with most programming languages. When you add many features to them, they become too complicated. So Go is investing in performance, safety, and tooling in a way that feels very Go-like, minimal, orthogonal, and deliberate. The feature looks bright not because Go is chasing threats, but because it keeps solving real problems with clarity and focus. I think we will see it used even more places, cloud system, edge, maybe even mobile, and continue to be a language that teams can rely on for the long haul.
That brings us to the end of the interview.
Yes.
Mihalis, thank you so much for joining us and sharing your experience and insights with us. It's been a pleasure having you with us.
Likewise, thank you very much, Stefan. Thank you very much for having me.
Right. And to our viewers, thanks for watching. If you'd like to dive deeper into the topics we've discussed, check out Mihalis's book, Mastering Go 4th Edition. It's packed with practical examples and hard-won insights from years of systems programming. You'll find the link in the description below. Until next time, this is Divya for Deep Engineering.